want to go over a group of reactions and review this entire process. So this little graphic right here, no, really stop writing, please, because we've got to be participating and learning what we missed yesterday. Awesome. Okay, so this summary is exactly the same as the summary that I have here on the board. Notice I've got combustion down lower. How do we tell if it's a combustion reaction? What is it about the combustion reaction that lets us know it's combustion? Yep. Oxygen must be on the left. Excellent. That's how we identify that. How do I identify if the reaction is synthesis? How do I identify if the reaction is synthesis? Jacqueline, how do I identify whether that reaction is synthesis? Well, if you pay attention, I can help you. No, you're actually writing today's note. I need you to actually write yesterday's note if you want to get caught up. But don't do that right now. You need to get caught up at lunch or something. How to identify whether it's synthesis? Yep. 2 becomes 1. Excellent. How to identify whether it becomes, or whether it is a decomposition? How do I tell if it's decomposition? One thing breaks down into 2 things. Excellent. How do I tell if it's a single displacement? Pat, what do you think? How do I tell if it's single displacement? The one letter switches with the other one. Well, I got letters switching down here in double displacement. So one thing by itself. What do we call it when it's one thing by itself? What type of substance is it when it's just got one type of atom in there? It's an element, and it's swapping with, what do we call it? Yeah, it's swapping with a compound. An element with a compound. Double displacement, compound, swapping with a compound. No need to write this, but let's identify these reactions. All right, and look at, I've got bullets and I've got numbers, it's chaos. First one, what type of reaction is that first reaction going to be? Eric, that first one, that's the bullet. What type of reaction is this? Single displacement? How do I know what a single displacement reaction is? Single displacement's down here. I don't have just one thing in a single displacement. 3 things. You should maybe pay attention a little more too. Might be a little helpful. Yep. Why is it decomposition? Yeah. One compound breaks down into 2 substances. That is a decomposition. Excellent. Decomposition. Decomp. Beautiful. Next one. What type of reaction is that? What type of reaction is that? Taking a look. Oh, Eric's going to redeem himself here. What do we got? Single displacement. Element with a compound produces a compound and an element. Single displacement is correct. What type of reaction is number 2 there? Number 2. Yep. Why is that? One thing becomes 2. You're right, it's synthesis, but your explanation is a little, what's on the left? How many things on the left? Well, you are. What's confusing you is all these numbers, I think. Don't worry about the coefficients when identifying the types of reaction. How many different types of things have I got on the left? So there's 2 different types of things. How many types of things are there on the right? That's all 1. That's a compound. So that's a synthesis because the 2 things are becoming 1. They're coming together. Propane plus oxygen gas to produce carbon dioxide and water. What kind of reaction is this? Yep. And why is that? Oxygen on the left. Combustion. And the products are carbon dioxide and water. This is combustion of a fuel. Excellent. Last one. What type of reaction is that? What type of reaction is that last one? Riley, what do you think? This last one here. Yeah, double displacement. Compound, compound. They've traded places. Double displacement. Excellent. Okay, let's now start on our discussion of acids and bases. So we are entering the last topic that deals with our chemistry unit. And we will be doing a little lab today to discover some of the properties of acids and bases. And then tomorrow we're going to talk about something called neutralization, and that is a special acid-base reaction. And we'll do a little neutralization tomorrow as a lab. And then on Friday we'll do kind of a culminating lab where we're going to be testing antacid tablets. Does everybody know what I mean by an antacid? When do you take an antacid? What's that? It stands for antiacid, correct. But why would you consume an antacid? It's an antiacid, correct. But why would you buy it and consume it? Yep. Heartburn or upset stomach. And does anybody know what the antacid does to relieve the heartburn? Any ideas? It kind of balances out the acids that are in our stomach that are used to break down the food. And sometimes when you eat too much, your stomach produces too much acid. It rises up into what's called your esophagus, and it feels painful. So you take the antacid to neutralize it. And so we will be testing antacids to see which is the most effective. All right. So acids and bases. You can see there's some pictures of some household acids and bases. Let's first talk about what an acid is. Yeah, you're writing this down. Now, I'm not going to be teaching you about the formulas of acids, but if we were to analyze the formula of all acids, they would all start with hydrogen. And it is this hydrogen that makes acids behave the way they do. So if you, if you tasted an acid, and we're not going to be able to do that, but there's many common acids that exist in nature, in many foods. Citric acid is an example of one. Where do we find citric acid? Yep. Yeah, citrus fruits. It's also found in apples and things like that as well. How about some other acids that we consume? Any ideas of other acids that we consume? Yep. Acetic acid. Excellent. What is acetic acid found in? Yeah, vinegar. What's common about the way those two things taste? Citrus fruits, vinegar. Yep. Careful, they're sour. They're sour. Bitter is a slightly different flavor, but they're sour. Now, that's a common thing about acids, and we're going to learn about some properties of the acids today. One of them isn't tasting them. We're not going to be taking our sulfuric acid and, squirting it into our mouths, because that would be dangerous. And the reason sulfuric acid would be dangerous is because it's a strong acid, where vinegar and citric acid are weak acids. Other examples of acids that we can taste are found in pop, all right? There's an acid in there called carbonic acid, all right? And that's what makes, when you drink a pop real fast, you know how sometimes it feels like it's burning the back of your throat? That's the acid doing its work. It's literally just slightly burning the back of your throat, and you can feel it, all right? Anyway, in each of those acids, if I were to write the formulas down for each of them, vinegar is C2H3O2. So there's the H. In the carbonic acid, H2CO3, there's the H. In the citric acid, I don't know the formula for citric acid. It's a very big molecule. It's a biological molecule. Anyway, the important thing is they all have H's in them. And when the H's, or when they're dissolved in water, the H's are released. And it's the H's that are going around doing their thing. Right? If you were to get an acid burn on your skin, strong acid on your skin, that burning skin, the reason it's burning is because of the H's. They're attacking the cells and breaking the cells down. Some other common acids. Hydrochloric acid starts with an H. That's stomach acid. Sulfuric acid. We're going to use some sulfuric acid today. That's battery acid. We're not going to use it at the same strength that you find it in a battery, but we will be using it today. Citric acid, found in citrus, lemons, orange. Acetic acid, found in vinegar. Carbonic acid, found in pop. Many, many other acids that go with that. Another use of hydrochloric acid. A common name for hydrochloric acid is muriatic acid. And if you have a pool at your house, and let's say you're opening the pool, and sometimes the pH needs to be adjusted, you can go to a pool supply store and you can buy some muriatic acid, put it in there and adjust the pH. So hydrochloric acid is often used in that sense as well. Okay, let's quickly talk a little bit about bases. So bases, instead of having H's in there, they have hydroxides. And we've seen the hydroxide ion. Actually, that negative is better off on the outside than it is on the inside. It would be more correct to put that negative out there than in there, like on our ion chart, right? We have a hydroxide on our ion chart. And it turns out that chemicals that can produce these hydroxides are basic. All right, now bases they don't seem to be quite as cool as acids, right? You know, if there's a movie or a television show, and let's say a soap opera, and somebody wants to get back at somebody else, you know, let's say I remember Days of Our Lives. My wife used to watch that, and the one sister was evil, and the other sister was, oh, she was so beautiful, and everything worked so well. So the evil sister took some acid and threw it in the face of the good-looking sister, and it was really horrific. You know, terrible special effects. But you know what I mean? Throws acid at the face of somebody. Oh, how mean can that be? Notice how they never throw a base. What did you do? I threw a base in your face. You know, it's like, what does a base do? Well, it's kind of like an acid, but it's like the opposite of an acid, but it's not as cool as an acid. See, for some reason, bases aren't as cool. I don't know why. They do react a little slower. If you were to get a strong acid on your skin, it would start to burn your skin fairly quickly. If you were to get the same strength base on your skin, it would still burn your skin, but it does it at a slower rate. So it's a little slower. Maybe that's why it's not so cool. It's slower at what it does. Bases also have distinct properties, and we're going to measure those distinct properties in a minute. All right? The reason acids go with bases is because they neutralize each other, and that's what we're going to talk about tomorrow. You can put an acid together with a base, and you can then make it safe because they cancel each other out. Okay? So sodium hydroxide, sometimes it's called lye. If you were to buy it, maybe you can sometimes buy that at a farm chemical store. What a terrible way to say that. Like at a co-op where you buy fertilizer and things like that. You can sometimes buy lye. Say you got a pH problem in your soil, you could spread that on the soil and it would change the pH. Also found in drain cleaner. Sodium bicarbonate is baking soda. All right. Ammonium hydroxide is window cleaner. We used a little bit of that yesterday in our lab. And potassium hydroxide is found in soap. Acids taste sour, but bases, if you've ever used, say, the toothpaste with baking soda in it, have you ever used that before? They sometimes say baking soda can make your teeth whiter. The Arm & Hammer toothpaste, how does it taste? A little gritty, and it's bitter. Bitter is the flavor of bases. Bases are bitter, all right? And acids are sour. All right? Again, I'm not sure where everyone is at. Some people are at different spots. So how are bases and acids made? Well, they're made from metals versus nonmetals, and we've seen that all the way along for quite some time. When you've got metals, something happens in a certain way, and when you've got nonmetals, other things can happen. So when a nonmetal is burnt, we burn it in air, and we take that stuff that's left, like the ashes, and we mix it with water, the nonmetals will produce acids. So these guys here, hydrochloric acid has chlorine in it. Carbonic acid and acetic acid has carbon in it. Nitric acid has nitrogen in it. Sulfuric acid has sulfur in it. Phosphoric acid has phosphorus in it. All right? So the nonmetals, when they're burnt and you dissolve whatever you have in water, you then produce the acid. For bases, it's the metals. Sodium hydroxide, potassium hydroxide. One that I didn't talk about, magnesium hydroxide. Magnesium hydroxide in water, you can buy it in the drugstore. It's called milk of magnesia. And you take it as an antacid. Again, you got an upset stomach, you take some milk of magnesia, it goes into your stomach, it neutralizes it. Calcium hydroxide. All of these things link with hydroxide and make bases. All right? Nonmetals make acids. Metals, when you burn them and you dissolve them in water, make bases. All right? These metals in here in the middle, they're not as reactive as those guys on the end. There is no gold. Well, you can have gold hydroxide, but it's not easy to make. It's something that doesn't get formed very easily, where sodium hydroxide is really easy to produce. Again, I'm not sure where everyone's at. People are at different places. Okay, so what we want to do now is we want to talk a little bit about how we measure acids and bases. Yep, we want to write this down. We're going to be using some test materials that allow us to determine whether something is acidic or basic. On each of the lab benches, there are 3 pieces of paper. One contains the acids we're going to test, one contains the bases, and the other contains the test materials, the things that we use to test them. Put a little bit of it in an acid, see what it does, put a little bit of it in the base. Many of these things simply change color depending on whether they're in an acid or a base. Litmus paper comes in 2 types. Blue litmus paper, which obviously starts out blue, tiny little piece of paper, and you're going to use this in order to do some tests. And when you use it, you don't need to use an entire strip. You can actually break that into 3 little pieces in order to do some tests with this, so that you got 3 little pieces, because we're just going to be dipping them in the wells. But there's blue litmus paper that has a certain color. There's red litmus paper that has a certain color. There's liquid versions of these indicators. Bromethymol blue starts out as blue. And we've already encountered one, phenolphthalein. We've used that in a couple of places. It starts out as clear and then has this pink color. Right? We've seen that earlier on when we did some other tests. Then there's also something here called pH paper. All right, and that's what my next slide is on. All right. So first, let's talk a little bit about what we mean by the pH scale, and then I'll tell you how the pH paper works. All right? The pH paper itself looks much like the litmus paper, except it starts out a little orangey. And again, they're just little strips. And with the pH paper, there is a special scale. It's on the inside of the containers, but I've taken some out so that you can see the scale nice and clearly. And that pH scale has a bunch of numbers on it. And I need to talk a little bit about what those numbers mean before we do the experiment. Now, for those of you who have written far ahead, I need you to come back to this spot, because I'm going to be writing on this scale some important pieces of information. For those of you who are writing right now, you're in a good spot. So pH. It's actually a complicated mathematical equation. It's used to calculate these H's and OH's that are in the water. In my grade 11 and grade 12, we do these calculations, but you guys don't have to worry about the calculations. You just have to know what the numbers mean. So, 7, right in the middle of the pH scale. Does anybody know what we call a solution that has a pH of 7? Yep. It's neutral. It means it's not behaving as an acid, nor is it behaving as a base. So right above 7, you can put neutral. That is a neutral solution. All right? Down at low pH numbers, 1 through 6.9999, whatever, 1 through 6. What type of solution is it? Does anybody know from previous experience? Does anybody know what that is? Yep. It's acid. So way down here we have strong acid. And as you get kind of closer to 7, we would have weak acid. And I think we can probably make a guess at what's happening on the other side. Logan, other side, what do you think's happening way up at 14? Bases. Strong bases. Or just put strong base. And in the middle here, weak base. All right? Okay? And when I say weak, so we got 0, 1, 2, 3, we're probably at like 4 or 5. So I'm going to say approximately 4 to 5, right? And then in here as well, 14, 13, 12, 11, probably at around 10 or 9, somewhere at around 9, we're talking about a weak base. All right? So what does the pH paper do? When we dip the pH paper into the acid or base, it'll become a certain color, and we can then compare it to the color on the chart. There it is right there. This is exactly the same chart that I have, except it's bigger. We call it universal indicator paper, or pH paper, and you simply have to match that pH paper in order to figure out what the pH is. So at this point, we're ready to do our lab activity. So I'm going to stop the video, and we're going to do some checking to see what the properties of acids are and what the properties of bases are. So again, I'm going to just stop my recording as I normally do. You guys can get ready with Google Classroom and find the